Okay, so the camera is recording as well. Okay, sorry about this. Okay, so I can how do I switch it to speaker view? But I'm speaking, so why is it switch to current speaker mode? Okay, but I'm speaking. Can you hear me? So why isn't it, okay. So why is it not, so it's set on current speaker mode, but now it's supposed to, okay, stop sharing. So I'm sorry about this, so somebody suggested sharing the screen because it makes the image bigger. I'm sorry, I haven't had time to figure out how to do that with this thing because now it's set on speaker mode, but it's showing me one of you. Even though I don't hear anybody else saying anything, you can hear me. I'm just going to go ahead and give the lecture and tell them afterwards that yes, I have the webcam now. I can't believe I cycled out. So Manju lives in Bedford, actually past Bedford. So I cycled out this morning to pick up the webcam because they're going to do the delivery tomorrow. And I wanted it for this lecture. And it's like 30 kilometers round trip. And I got home and I had like 10 minutes and I plugged it in and it doesn't work. So we could do this by Zoom because Zoom can apparently find the camera. But we can't do it by Collaborate Ultra, so I'm back to having the another little camera on a tripod sitting behind my laptop. And this I can't do either. But we're going to forget about the technology and I'm going to teach you algorithms because that works and it's something I like. Okay, but it's a beautiful day. And it was actually, Bedford Highway is not the best ride in the world, but... So just checking again, you can hear me. Okay. Okay, so I'm actually going to share my screen for a second. Not for, the entire screen. You have to, even though it's the entire screen, you have to click on it. So we're going to talk a bit more about knapsack because it's a classic problem. And last week we saw sort of three versions. We saw binary knapsack, which is you can take the thing. Fractional knapsack, which is you can take the thing and you can cut it later. Okay, so you can, all the stuff you can cut to optimally fill your knapsack. And then we talked about binary knapsack, and then we talked about binary knapsack with uniform densities. And we saw that binary knapsack, it's harder, the greedy algorithm doesn't work, it doesn't give you an optimal solution, but then we saw that for uniform densities, if you take the biggest thing first, you get at least a two approximation algorithm. And the thing, we don't actually have a polynomial time algorithm for knapsack. And it's strongly believed that it doesn't exist. So, this cartoon is a bit misleading. So it's not the best cartoon, it's not the best drawn cartoon. But on the left, you have a list of appetizers. So it's supposed to be a snapshot of a menu. And then on the right, so it's above it says my hobby embedding NP-complete problems in restaurant orders. Now, NP-complete, okay, so some of the notation is slightly, okay, just read hard for the moment. On the right it says we'd like exactly 1505 worth of appetizers, please, and the server says exactly. Okay, here these papers on the knapsack problem might help you out, and it says listen, I have 6 other tables to get to as fast as possible. Of course, want something on traveling salesman, which is another NP complete problem. We may have mentioned it when we were talking about Hamiltonian path, right? So, this problem, let's consider this problem. So, what you have is a bunch of numbers, and then you're asked if you can. So you have a bunch of appetizer prices, and you're asked, can you find a combination of these, and you can order multiple of the same thing in this particular case, such that the prices sum to exactly 1505. This is not fractional, okay? This is binary in the sense that if you order a side salad, you get a whole side salad. You can't say, I would like a quarter of a side salad, and I would like to pay only a quarter of the price of a side salad, okay? I don't think I know many restaurants where you can do that. So, as you get from this cartoon, this is supposed to be difficult, okay? It's like binary knapsack, binary knapsack in the sense that either you take something or you don't. So I've told you that we don't know how to do this in polynomial time. Now I'm going to show you an algorithm for it. But this is going to start off our new section of the course on dynamic programming. Okay? So I'm just going to write down. I could try to do this thing where I could share this window with you, and I could go back to the Collaborate Ultra, but I'm just going to write down the prices, 215, 275. 275, 335, 335, 355, 420 and 580. 420. Okay. Yeah, hi. Are you still there? I have only 28 people? Okay. Still there? Why is it... I don't want to show my screen anymore. Why is it doing this? You are sharing an application. No, I'm not. Stop. Okay. So, is anyone there? 27? I just lost somebody. Okay, good. So you want 1505. So there's a problem. Oh no, let's not talk about that because the assignment is due tomorrow. So there is something on there about a greedy algorithm for making change. But I think I asked you for the algorithm, so let's not use that algorithm and see that it doesn't work here. So how would you do this? Okay. Well, let's consider some smaller numbers because the first thing you would do is divide by 5. Okay, to make these. But let's suppose that we had 4, 3, 12, and 5, and we wanted to know if it was possible to get exactly 22. Okay? So, With dynamic programming, one of the things you frequently do, well, essentially you always do, is you build an array. Okay? Does anyone know how to do this? I mean, quickly? Supposedly quickly. Okay, so what I'm going to do is build an array. Let's say A. So this is going to be one-dimensional dynamic programming. So let's suppose that these are the costs of some appetizers. This is an expensive appetizer. And here, so this is A, and it goes from A0 to A22. And we want AI is true if we can choose appetizers to get total price exactly I. Okay? So, interaction. Can we choose appetizers to get total price? Excuse me. Total price exactly 0. Somebody. Yes, we can. So this is true. Or okay, yes. Can we do it with price exactly 1? No. So yes, no. Price exactly 2? No. Price exactly 3? Okay. So we can see that because 3 is that price. But let's think about how to do this algorithmically before it starts. Okay, let's just keep going for a second. So this is 3. 4? Yes. 5? Six. We're allowed to reuse them. Yes. Okay. So 6, we don't have an appetizer that costs 6 whatever cents, dollars, units of exchange. But we do have something that we'll get that has price 3, and we can just take 2 of it. So what we can do is look back Okay, so we can add 6, we can look back, well, we can look back 12, and this would be, is there something that gives us price minus 6? No. There are no appetizers for which G. Oh, okay. Oh, math. Maybe just keep aside, yes. Okay. Then we look back 5, but this is a no. So if we could get $1, then we could get 6 by taking whatever got us the $1 plus the appetizer that cost 5. So then we go back 4, and we get a no. But then finally we go back 3, and we get a yes. So, okay, so however we can get an order that costs $3, we can then add an appetizer that costs $3 on top of that, and it will then cost $6. Woo! So, let's do 7. Oh, I'm going to run out of time. So, 7. We look back 12, minus 5, no. We look back 5, so 2, no. We look back 4, and we see a yes, which is 3. And also, we look back 3, and we see another yes. So actually, we can do this by either taking an order of 3, and then adding a 4 on it, or taking an order of 4 and then adding a 3 on it. So, this is, what is 7? Is 7 a yes or a no? Anybody? Yes, good. I like being reassured that there's somebody still there. Okay. 8. Well, we look back 12, no. We look back 5, yes. We look back 4, yes. We look back 3, yes. So this is definitely a yes. And then 8, 9, we look back 12, no. 5, yes. 4, yes. 3, yes. So basically we can probably, we can actually keep doing this. So this, I just made up this example. So when we get to 22, it's probably a yes, because now that we have a row of yeses, at least 3 long, we can just keep adding 3, so it's definitely going to be a yes up here. So, this is going to be so it's times 2 divided by 10. This is 106. This is 84. This is 71. This is 67. This is 55. And this is 43. So, and this would be times 301. Okay, so that's just getting rid of one of the decimal places. Okay, so now, if somebody gave you these numbers and said, okay, can you choose a subset of these that sums to exactly this? How would we do it? Well, we would say, okay, if we have a language that has booleans, we would say bool A, it's, well, okay, so this isn't actually, so it's 0 to 301. So normally you would, so you declare it a size 302. And then A0 equals true. And for I equals 1 to 301. Can you read this? Not really. Shoot. Okay. Oh, so the only thing that the new webcam got me was wasting 20 minutes of class and like 2 hours biking into Bedford. So, okay, bool A 0 to 301. Okay? Better? Okay. And then you're going to say A0 equals true. Because you can order no appetizers and they will charge you 0 unless they charge you cover and stuff like that. So then for I equals 1 to 301, this is going to clash. Do you all remember that AI is true if we can choose appetizers to get total price exactly I? Okay, that's how this is defined. So what we're going to do is, oops, I want another array, okay? So this, can you still read this up here? Okay. Int p equals 43, 55, 67, I hope I did this multiplication right, 71, 84, 106. Okay? So, for j equals 0 to 1, 2, 3, 4, 5, 6, what do we do? Since you all like these curly braces. Random victim again. Logan Sutherland. Mohammed Ramazani, are you there? Logan Sutherland. Yes, okay. Mohammed, do you have a microphone? P. Okay. It's because I just multiplied. I didn't want to deal with 3-digit numbers, so I just multiplied everything by, I just divided by 5. Well, actually, I multiplied by 2 and divided by 10, which is the same thing. So it's like 43 is because 21.5 divided by 5 is 43. Yes. Okay. I just like 2-digit number. This is still a 3-digit number, but it's slightly smaller. So this is, yeah, okay. Sorry, yes, okay. So, yes, it's 580. Oh, right, sorry. That would mess things up. Okay, so, Mohammed, are you still there? Do you have a microphone? Could you turn your microphone on? Hello? I can't hear you. Do I have my volume on? Can anybody else hear? I can't, wait, one person can't hear. I can't hear anything, but somebody can hear. This is weird. I can hear. He's not on mic. Okay, you can hear me, but can you hear Muhammad? No. Muhammad, say something. Speak to us. Can somebody try their mic? Okay, but can somebody try their mic? Okay, but I can't hear anything. Devin is saying something, but I can't hear it. I get a spinning circle. Do I have to allow people to use wait, now I vaguely hear something. Maybe? Okay.
No, there we go.
Yes! Yay! Okay, so I'm sorry, but so you're the only one I can hear, so you have to tell us what to do next. Sorry. So, A0 is true. We can make an order of appetizers that has price exactly 0. Then, for I from 1 to 301, we're going to do what we just did and look through all of these. So, what do I write now?
Multiply j by the values of p.
Well, I'm just going to use this as an index. So, well, the first thing, okay, so Gabriel wrote it. The first thing, we're going to do what Gabriel just wrote, but first we're going to check if I minus pj, maybe I should make this bigger again. Can you read this? Oh, right, so that's what if I minus pj, first we're going to say it's greater than or equal to 0. And AI minus pj equals true, then what? Yes. Okay. Then AI equals true. This online learning stuff is not fun. Okay. So we do this check so that we don't get a say fault. Okay? Okay, yes, AI is true. Because if we don't do this, if we don't do that check, then we're looking before the array, and that's bad, and your computer will complain. If this is greater than or equal to 0, and this is true, then, sorry, I'm missing a bracket here. Then it means we can get, for some pj, we can get an order that makes exactly the price we want minus whatever this price is. We can get that, so we can get price I, right? So then for and then we say this closes the if, this closes the for, this closes the for. And then we print A30. So this